record the class lecture.
Is
Ok,
it visible, right?
bienvenido al coloquio del Departamento de Matemática, UDEC. Hoy tenemos profesor Vidhan Chandra Sardar de Departamento de Matemática in the Institute of Science, Roper. Ya, el tópico de su charla es Homogenization of Optimal Control Problems Governed by Stokes Equation. Y Vidhan, you will have something like 50 minutes, and last 5 to 10 minutes we keep for the okay, or comments and anything. Yep.
Yeah, sure. So my slide is visible, right?
So yes, so slides are visible. Please go on.
Okay, so thank you very much, Dr. Ravi Prakash, for the invitation. So in this talk, I'm going to discuss about the homogenization of optimal control problem governed by the Stokes system. So which will be defined on some oscillating domain. So first I'll start with what do you mean by the oscillating domain with two model domain. So the first domain, so this is the domain oscillating domain. So I'm going to describe later on in the next slide. So this is the domain oscillating domain. In the top part, you can see that there is a fixed base part and there is a pillar in the top part of that. So there is a similar type of domain that instead of pillar type, that it's called that smooth domain, that called the smooth pillar type domain. In the both the domain, I'm going to consider the optimal control problem corresponding to the Stokes system. So let us first consider the Stokes system in this, that in the left hand side, the pillar type of domain. So first we'll understand what is the domain is oscillating meaning. The more details, the domain oscillating omega epsilon, it is a consist of fixed part, the omega minus, it is the base part, and the oscillating part omega epsilon plus consists of slabs of height h2 minus h1 and the breadth a epsilon into b minus a. So here the parameter epsilon is equal to 1 over m. M is denote the number of slab. The domain is oscillating in the sense that whenever the parameter small parameter epsilon go approaching to 0, so then the number of slabs are increasing. So in that sense the domain is oscillating. So here is a few notation. So I will going to use that gamma epsilon, it is the top oscillating part of the boundary. Okay, and the complement that gamma is in the side part, the bottom part is that gamma b. So in this domain, we are going to introduce the optimal control problem. First, I look few literature that studied regarding the optimal control problem. The here that optimal control problem corresponding to the Laplace operator. In the first two references, here we discuss about the optimal control problem corresponding to the Laplace operator, but the controls are acting on the fixed part of the domain. So one of them, it will be on the boundary part of the domain, that on gamma b, the boundary control problem, and another problem where the control is away from that oscillating part, means away from omega epsilon plus. So here the both the article concerned with that. And after that, then we have studied the optimal control problem whenever the control applied on the oscillating part of the region. Either it is in that oscillating part of the boundary or it is in the oscillating interior control problem. So in this next two article we have studied earlier. So and the corresponding, so all the four article here corresponding to the Laplace operator. So next I move into the optimal control problem corresponding to the Stokes operator. Okay, here. So here the optimal control problem. So just a minute. Okay. So here the optimal control problem that we have studied correspond. So the authors have studied corresponding to the Stokes operator, where the control is away from that oscillating region. That here you can see that theta is the control acting on the fixed part of the domain omega minus. When the small omega, it is the properly subset of on omega minus. And we have studied that limiting analysis and that obtained the result the corresponding to the corresponding Stokes system in a fixed domain. Here there is no contribution coming from that oscillating part of the region due to mainly that here the authors consider the Dirichlet boundary condition on the oscillating part of the boundary. So that means I said the u epsilon is equal to 0 on gamma epsilon. So therefore, there is no contribution on the top part of the region. So now we are going to consider in that oscillating part of that boundary, interior control problem, corresponding to that more general Stokes operator. Okay, so you are interested to find out that. So okay, so we are interested to apply the control on the oscillating part of the region. So first we'll take a theta which is defined in a reference domain. So reference cell here, that lambda plus. So where the height is fixed h2, that h2 minus h1, and the breadth is that b minus a, right? So here we take the control theta, and then we do the scaling, and using periodicity on the x1 direction, we apply the control on the oscillating part of the domain. Fine. And then we consider this following optimal control problem. So this is the standard quadratic cost functional, where the control coming from the fixed reference cell. Fine. And that u and that u epsilon, they satisfy this Stokes operator u epsilon, and p epsilon is the corresponding pressure, and theta epsilon is the scale form, which is defined on the oscillating part of the domain. So we need the divergence free boundary condition. The divergence of u epsilon is equal to 0. And we introduce, so we define that Neumann type of boundary condition on the oscillating part of the domain, and the rest of the boundary you have the Dirichlet boundary condition. And here, to study this problem, first we need some condition on that coefficient aij. As usual, we need uniform ellipticity constant as well as the uniform bound. And then we have the existence and uniqueness of this problem for every epsilon. Okay, and this problem, okay, and this problem, it is that first have that introduce this generalized Stokes operator. So okay, so in the, I'll show you that letter book. So this is the corresponding weak formulation for the Stokes system. So which will satisfy both this equation, and this is the corresponding weak formulation. Our main aim is to study as epsilon tends to 0, then what will happen, then how do you find out the limit control problem. Okay, and that this type of operator, the generalized Stokes operator, one can found in this reference. So this is the pioneer book that by Benesians, Lyons, and Papanopoulos, asymptotic analysis for periodic structure. Okay, so for our problem, so first we need to study that for every fixed epsilon positive, we need to have that that optimal control admits a unique solution. Let's say the optimal control we denoted by theta epsilon bar. And the next question, after proving this result, we need to find out that what will be the characterization for the optimal control theta epsilon bar. Fine. To do this characterization, we are going to introduce that we are going to use the especially the unfolding operator here. So first I'll define that what is unfolding operator. So this is the definition of an unfolding operator, the T epsilon, which is defined in that oscillating domain omega epsilon plus. So if you have any function which is defined in the oscillating part of the domain under unfolding, it is taking the extra dimension. It will have the extra dimension omega plus cross UV. And this unfolding operator has introduced in this paper that Demdeman and the Peterson homogenization of oscillating boundaries. And this unfolding operator has interesting properties, like this unfolding operator T epsilon, it is a linear, and it is that if you take the multiplication T epsilon of UV, it will preserve the multiplication T epsilon of U into T epsilon V. And for if you have that any function U in that oscillating part, so under unfolding, we have this integral equality. Okay, and we are going to explore this integral equality. We are going to extensively, we are going to use it. And the next, the property number 3, that if you have any function which is on the H1 space, the under unfolding, it will belongs to this kind of Sobolev space, this kind of spaces. And we can also talk about the derivative, that del by del x2, then we can interchange. So both the property we have it. Okay, and we also need some convergence result for the unfolding operator. The first, that if that u it is defined on the fixed domain under unfolding, so it will go to the strong convergences in the appropriate space. If you have the strong convergence under unfolding, again we'll get that strong convergence. And the property number 3, if you have the weak convergence under unfolding, then we can get that that u epsilon extended by 0 will get that weak convergences. And all this property will help us to pass to the limit in the weak formulation of our optimal control problem. All right. And okay, fine. So this is the characterization of this the optimal control problem. In our case, the theta epsilon, the optimal control, we have find out using this unfolding operator, where this is the adjoint state corresponding to our the Stokes operator. Fine. And this characterization, it's not new. Earlier we have find out that earlier our work for the Laplace operator, we have obtained that unfolding operator. We have characterized using the the optimal control using that unfolding operator. So now you have to move into the next step that we want to pass to the limit. For that we need some uniform bound that if theta epsilon is the optimal control, so you'll have that this uniform bound, the theta epsilon and the L2 of on that reference cell, and see it is a generic constant. This is the independent of epsilon, and we'll have we need this bound U epsilon bar. For P epsilon bar is the corresponding pressure, and the corresponding the adjoint problem V epsilon bar and the Q epsilon bar. To prove this uniform estimate, we need few lemmas, the few inequalities like standard Poincare inequality, that we also need that Bogosky operator theorem, and I'm going to discuss it now. The first from the a priori estimate of this Stokes operator, we'll have this estimate that U epsilon under this subloop space plus P epsilon bar. Then we'll get a constant in general, that the constant C, it will depend on the domain omega epsilon. Fine. So we need to have the uniform estimate, and to obtain the uniform estimate we need this Poincare inequality that in our oscillating domain. So then we'll get that the any function which is in this space, then we'll have that L2 norm which will be bounded by the gradient norm, where the constant C, it is independent of epsilon. Okay. And and we also need another estimate. It's called the Bogosky operator type of estimate, and it is saying that the classical Bogosky operator is saying that if you have that any function which is in L2 with average is 0 on omega, so then we'll find out a function V which will be an H0 on omega, for which will solve the divergence problem. The divergence of V is equal to 0 on omega, and we'll also have this estimate that V on H1 norm will get a constant which will be dependent on the domain and the dimension with the bounded by that G in L2 norm. The similar type of Bogosky operator type of result we obtained in earlier in our work, that for every P epsilon positive, so you should find out the key epsilon in L2 of omega epsilon. So we will get a function f of epsilon for which we'll solve this problem. The divergence of f epsilon is equal to key epsilon, and we also have this estimate. And this estimate and earlier the Poincare inequality. So using these two, we'll get that uniform bound for U epsilon. So after using that, both the result, then we'll get the uniform bound for U epsilon, P epsilon, and the theta epsilon bar. Okay, and now we know that due to our geometry of the domain, if you remember that in our domain omega epsilon is the consists of two part, and the fixed part omega minus, and we have that oscillating region omega epsilon plus. So difficulty is that, so in the oscillating part we cannot extract a convergence subsequence. So we going to use that unfolding operator. So first we'll write down on omega minus, so that we will restrict that U epsilon the solution on omega minus. So which will be bounded that H1 on omega minus, bounded the uniform bound, so we can extract two convergence subsequences. So now for the case of that on that oscillating part of the domain, so we are going to use that unfolding operator to get the estimate in a fixed domain. So here is the estimate. We'll get T epsilon of U epsilon plus, and using in this space, and which will be again uniformly bounded that U epsilon plus, here it should be bar, uniformly bounded, and then we'll have the two convergence subsequences. Okay, so using this and similarly you can derive from P epsilon and the corresponding the adjoint problem, and we can pass to the limit in our weak formulation. So that part I'm skipping, I'm not going to show it here. And then we'll obtain that finally the limit system for this problem, that this is the limit problem on omega plus. We obtained this equation that if you observe that in omega plus, so there is no pressure term is involvement. Fine. And that omega minus, as usual, we obtained that Stokes system, the generalized Stokes operator, and we have that appropriate interface condition. And if you see that, and that in the interface, the pressure term is appearing P minus on the interface. Okay, and then we need to also have to study this limit system have the existence and uniqueness. Yes, we can also prove that existence and uniqueness of this problem, and we also introduce the limit optimal control problem in the fixed domain. So okay, let me tell. Okay, so here that matrix B is appeared here. So this is the form we obtained, the matrix B, and we can prove that the B is this that B, it is also the uniformly elliptic. Using that A is also uniformly elliptic operator. Okay, so this is the corresponding limit control problem, means this is the appropriate cost functional we have introduced here, and then we can study this optimal control problem. And first we need to show that existence and uniqueness of the optimal control problem, and we can also characterize this problem. Fine. Now I'm going to show you the main convergence result we have obtained in this problem. That so this is the convergence result we have obtained, that at the epsilon level we have that optimal system. At the limit system we also have that optimal system. Now we are going to showing that in this result that optimal control converges to the optimal solution. Right. So first here that we obtained that weak convergence for this optimal control, the theta epsilon bar weak converges to the theta, and then the solution, that velocity profile, that u epsilon plus on the extended by 0 will have some appropriate weight b minus a into u bar, u plus bar, and that corresponding also that the derivative convergence. So here the more interesting convergence I'll show you here, and that okay, yeah, that if you observe that del u epsilon plus by del with respect to the x1, which is converging to that the solution u, the second component del u2 plus by del x2. Okay, and that x2 derivative here, fine. X2 derivative is fine, so because there is no oscillation on the x2 direction, so this is expected, this convergence result at the end. And then corresponding the convergence for pressure, so this is also another interesting convergence result, that p epsilon bar, the pressure which is defined on the oscillating part of the domain, will get a convergence in terms of the velocity. Fine, and that in that fixed part, so there is no oscillation, so then we'll have that weak convergences and the fixed part, and where this is the theta bar corresponding in this form. Okay, fine. So now I move into that another problem that as I said, so this is that we have studied the interior control problem whenever it is defined on that oscillating part of the region. Now I'm going to introduce that another control problem. It's called the boundary optimal control problem. Instead of that so now I'm going to introduce that in the oscillating part of the boundary for the smooth oscillation. Okay, so this is the domain that here are like unlikely. So here we have the smooth oscillating domain, then the top region. So we're going to introduce, so this is with our reference cell. Here we'll apply the control here for the fixed reference cell, and then we extended periodically, and we defined the control here on the oscillating part of the boundary, that gamma epsilon. So in this introduction, so in this case, okay, so let me show you that how we can define it for more precisely. So we'll start with the theta that will in the reference domain, and we'll use that some scaling, that epsilon power alpha, and we define the theta epsilon again in L2 gamma itself. So in this fashion, so where you can see that that appropriate weight, the tau epsilon is defined here. Okay, so you need the initial that condition for eta as well, and that we also have that appropriate weight multiplied that epsilon power alpha, where that alpha is greater than is equal to 1. And we're going to show you that in this control problem, that for different value of alpha will get a different that limit control problem. Okay, so this is the optimal so okay, and then we have extended into that oscillating part of the domain periodically. And this is the optimal control problem we have considered in that in the 3 dimension in R3, corresponding to the Stokes operator. Fine. So here we have applied the control through that Neumann boundary condition on that oscillating part of the domain, and the optimal control corresponding to that quadratic cost functional. Okay, so and we obtained the result. First we shown that the existence of that uniqueness of this optimal control problem, and we also have given the characterization of the optimal control problem. And this characterization of this optimal control problem, we're going to use that the unfolding operator, And this unfolding operator, we need the generalized unfolding operator. So this unfolding operator introduced in this article. And using this unfolding operator, the generalized unfolding operator, we have the characterization of this optimal control. So it is given in this fashion. So here the notation we may not. So for the notation, we need to check our article. And so this is that characterization at epsilon level. Okay. So, and here that V epsilon bar, it is the corresponding adjoint problem. And now, so this is the corresponding the limit system that for alpha is equal to 1, we'll obtain this control problem. This is the limit system. And we will see that for alpha is equal to 1, though we'll see that alpha is equal to 1, we'll have the control is appearing and that omega plus, as well as in that in the upper boundary, the gamma u. So this will be the control term, as well as that we'll also have that interface control term. So for alpha is the critical case, that for alpha is equal to 1, we'll see that though the control is applying in that oscillating part of the boundary, but in the limiting process, we'll obtain in the upper part and in the top part of the boundary, as well as in the interface, as well as that control is distributed throughout the boundary in that upper part. And lower part, will as usual, we have the Stokes problem with the divergence condition. Okay, and for alpha greater than 1, so there will be no control on the oscillating. So in that red, the control, whatever interior control, there will be no control. So you also have studied in this article that how to show, we have shown that optimal control problem, it is convergence to the optimal solution. Okay. So now I'm going to show you some few references, and the first references we are used to study that. So here in this book we have also find out that that Neumann type of boundary condition that corresponding to that Stokes operator in the first book, and then in the second article it is discussed about that unfolding operator, the first introduced in the fixed domain, the Serensky, Damelin, and Grisho in 2002. And this unfolding operator also that in the corresponding to the oscillating domain. So there are few more literature studied, and the strong contest of diffusivity in the third article. That, and if you look at that, and also this unfolding operator also that studied that semi-linear optimal control problem for the smooth circular type of domain recently, and few more article here. Okay, so one article probably have repeated. Okay, last article. So this is the more recent article that where the authors have discussed the homogenization of nonlinear monotone problem with the locally periodic domain via the unfolding operator. Okay, so with this, thank you all. Yes.
Thank you, Vidhan. Anybody comment? Any question? Yeah, Rajesh,
So,
you want to say something?
what are the outstanding?
Yeah.
So, what problems are there to be solved in this kind of area? Meaning,
Hello. Okay, so one problem that, so here
yeah.
in the first, when you apply that interior control problem, so here in the generalized Stokes operator, we considered in the beginning that operator, the coefficient Aij, which is independent of epsilon, we consider. So that's still this problem we are trying, that if the coefficient is depending on the parameter epsilon, that how it will be the limiting system that for this generalized Stokes operator. So this problem, and another thing we are trying that, so we have shown the result for that interior control problem for the in a 2-dimension. In the 3-dimension, we obtained the result, but we are not able to write down explicitly the how that the limit, the coefficient, how it will come that appear the matrix B, and to prove that the ellipticity of that coefficient, that matrix, the uniform bound. So that part we are in progress. Yeah.
Thank you.
Yeah, sure.
¿Alguien más que quiere preguntar algo? Yeah, if not, I have a question. How will you explain the disappearance of the pressure term in the limit problem? It means it just disappeared. How will you explain this physically? How this pressure term got converted into the U?
Pressure term physically, so due to the Neumann boundary condition, that Neumann boundary condition, it's
So,
also say that, okay.
Mathematics I understood. I want to understand how
Okay,
physically
so
you explain.
basically this is actually, no, that's what I'm saying. The physically it's scale that no flux type of condition, that Neumann type of boundary condition. So
Yeah. But and more interestingly, this term, even if the periodic control, interior control was there, then nothing happened in the limit. Limit problem was independent of the control in the upper side, right?
right.
That thing is also happening because of what? Because of the coefficient dilation is not appropriate or what?
Okay.
Because you see in the boundary control you have got something right on the in the upper part, but in the
Right.
interior
The
control
boundary
you did
control
not
we've
get
got
anything.
right. So in the
So
interior,
it means there is some dilation issue is happening.
okay.
Yeah, we can talk later. Anybody, alguien más que quiere pregunta? Everybody else can ask if they want. We have enough time actually. We have 30 minutes. Si no paramos acá. Thank you very much, Vidhan, once again. It was a
Sure.
nice talk.
Thank
I
you.
liked
Yes.
that article is of yours with Professor Muthu Kumar, right? Or no?
Okay. Yes, Muthu
This
Kumar.
article is Muthu Kumar. Where did it appear?
Which one?
This article which you just presented, the first part.
Okay, first part. The first part is okay. This is in that in the review actually, that integrate, and the boundary is already published, that with Abu Sufyan.
Okay. This is the work by with Abu. Yeah.
Oh yeah, yes.
Okay, so the second part is still under in review.
Right.
Okay, the interior control. Okay, thank you
Interior.
very much. It was nice.
Okay, thank you.
Yeah.
Thank
So see you.
you. Yes.
Bye
Yes,
bye.
thank you. Yes, bye.
Ciao todos.
See you. Bye.